Hello students, now we are going to discuss what is the role of signed curvature, how much it is important. So this is the objective of the class. As I mentioned earlier, a unit speed plane curve is essentially determined if the signed curvature is known at every point. That means if you know the signed curvature, you can trace the curve. Wow, it is the other way around we actually computed so far. If you know the curve, if you know the parameterized curve, you can compute its signed curvature. That is what we have done so far. Now we are reversing the situation. Suppose we are given only signed curvature, then we can plot the curve. That's what. If the curvature, that means how much the curve bends, that is given to you, and it is the signed curvature that is given to you. That means signed means negative or positive. So positive signed curvature means curve is traversed in the counterclockwise direction. That means the tangent vector rotates counterclockwise. And signed curvature is negative means the tangent vector rotates clockwise. That means the curve also rotates clockwise with respect to increasing value of the parameter. So if you know the curvature, how much it curves and in which direction, we can determine the curve. But the thing is, suppose the curvature is given to me and this is the curve I have obtained after using this technique. Okay, another person can traverse something like this. Oh no, another person can travel like this. Another person can travel something like this. Okay, so in all the cases the signed curvature is the same, but the curves are not the same. So what is meant by determined? The curve is determined if the signed curvature is known. So it is actually up to, not unique, but up to an isometry of R2. That is what essentially means. The curve is not unique, it is up to a direct isometry of R2. So what is meant by isometry? Isometry means distance preserving. Isometry means distance preserving. So can you give me distance preserving maps in R2? For example, translation. Translation is distance preserving. Suppose that this plane is translated to here. That means this point is translated to this point. Similarly, correspondingly, each point is translated to corresponding points here. So is this distance preserving? Of course, because if I take 2 points here and take their images will be here and here, the distance between this and this is the same as the distance between this and this. So translation is a distance preserving map, so it's an isometry. And now can you give example of another isometry? Yes, come on. What about rotation? They are also distance preserving. So a point here is rotated through an angle and it reaches here. The whole plane is rotated through an angle theta. theta degree rotation. The whole plane is rotated through an angle theta degree. So what are the new coordinates? It will be this, and this is the new x-axis, and this will be the new y-axis. This is the original x-axis, this is the original y-axis. This much angle is theta, rotation through an angle theta. Is this distance preserving? Let us check. If you take 2 points here and here, this is the distance between them. After rotation, the new points, suppose here and here, these are the images. The distance between this and this is the same as the distance between this and this. Okay. So rotation, that is another example of a distance preserving map. And what about the combination of this and this? That means rotation and translation. Combine them. One after the other. First rotate and then translate. Or the other way around. First translate and then rotate. Are they the same? Yes, come on. You are at the origin. Walk 1 unit in this direction and turn through an angle, let us say theta. So you are here. No. Control Z. Yes. Walk let us say this much distance in this direction and then rotate through an angle theta. So you will reach here. Okay. Let us do the other way around. You are here. Rotate through an angle theta first and then walk this much distance. So you are here. So whether you are rotating first and then walking, or whether you are walking first and then rotating, the effect is the same. You will reach the same point. So rotation followed by translation is the same as the other way around. Translation followed by rotation. Translation followed by rotation. So suppose so the essential point that we are going to discuss is, suppose that this is the curve I have obtained. You can translate it to any other point. Yes, they have the same signed curvature. I am getting this curve. This is my curve, and this is your curve. I am given the signed curvature and I plotted this, and you are given the signed curvature, but you have plotted this curve. You did, because you are standing at some other point. You are standing at some other point and you started plotting your curve from that point. So you got something like this. Starting from here, like this, you traversed and reached here. You are also turning counterclockwise. I am also turning counterclockwise. A third person, he can rotate through an angle theta degree, and he can get something like this. This is his curve, his or her curve. So third person. Because he was standing here, looking diagonally. So he started like this and reached here. So essentially everyone has the same signed curvature for their curves. This is what the theorem says. I think we will state it here, and proof we can prove in another video. So theorem, theorem. So you are given the signed curvature. Let it be, you are given a function that is going to be the signed curvature of some curve. That is what our objective is. So let k be that given function from alpha beta to r, be any smooth function. Then there is a unit speed curve. Then there is a unit speed curve gamma from alpha beta to r2. That means it's a plane curve. Whose signed curvature is this given function k. Whose signed curvature is k. Further, now regarding uniqueness. As I mentioned, it's not unique, but it is unique up to an isometry. But further, if gamma tilde, this is your curve, from alpha comma beta to r2 is any other unit speed curve whose signed curvature is k, is the given function k. That means our my curve and your curve have the same signed curvature, which is that given function. Then what is the relation between your curve gamma tilde and my curve gamma? Then there is a direct isometry. They are related through this isometry. M of R2 such that gamma tilde of S is equal to M of gamma of S for all S in alpha beta. So this is my curve. I am applying an isometry and getting your curve. Similarly, the other way around also. You are starting with your gamma tilde, and from your gamma tilde you can get my curve gamma. How? Here I have to do a rotation and a translation. You also have to perform a rotation and translation to get my curve gamma. So if translation is obtained by means of a vector A, that's what I am doing, then your translation is going to be translation with the help of the vector minus vector A, minus of that of me. And if my angle is theta, then your angle for rotation is minus theta. നിങ്ങൾ ഒരു സ്ഥലത്തേക്ക് യാത്ര ചെയ്ത് പോവാണ്. തിരിച്ചു വരാൻ എന്താ ചെയ്യണത്? വലത്തോട്ട് തിരിഞ്ഞ കർവുകളൊക്കെ ഇടത്തോട്ട് തിരിയണം, ഇടത്തോട്ട് തിരിഞ്ഞ കർവുകളൊക്കെ വലത്തോട്ട് തിരിയണം, മുമ്പിലേക്ക് പോയതൊക്കെ പിന്നാക്കം വരണം. റൈറ്റ്? സോ യു വിൽ റീച്ച് ദ ഒറിജിനൽ പൊസിഷൻ. സിമിലർലി എൻ്റെ നിന്ന് നിങ്ങളുടെയിലേക്ക് പോകാൻ ഞാൻ തിരിഞ്ഞു മുൻപോട്ട് യാത്ര ചെയ്തു എന്നുണ്ടെങ്കിൽ നിങ്ങൾ പുറകോട്ട് യാത്ര ചെയ്യണം, ഞാൻ തിരിഞ്ഞതിൻ്റെ ഓപ്പോസിറ്റ് ഡയറക്ഷനിൽ തിരിയണം. That is also another isometry, right? Okay, so this is what we want to prove. Its proof will be in the next video. Thank you.